Engineered Geothermal Systems, or EGS, refers to a set of concepts that utilize rock stimulation techniques, also known as fracturing, to increase the amount of permeability in rocks. EGS, along with closed-loop systems, are typically referred to as scalable, or hot-dry rock geothermal, because the techniques, if perfected, could scale and feasibly allow geothermal energy to be produced anywhere in the world. EGS concepts can involve single or double well systems, and cutting-edge designs incorporate directional drilling and multi-stage fracturing techniques from the oil and gas industry in the quest to reduce cost and increase efficiency and output. So, what are the technological challenges associated with EGS, and what technologies and methodologies can be deployed from oil and gas to help drive down cost? What are the risks associated with these systems, and how can they be mitigated? Where in the world are there functioning EGS systems and new projects in development? Let's explore.
Good morning, good afternoon, good evening, depending on your time zone. I am Dr. Rita Okorafor, and welcome to this Pivot 2021 session, Getting to Geothermal Anywhere, EGS Technoeconomics. So I'm Dr. Rita Okorafor, the moderator of this session. I'm a postdoc with Stanford University. Prior to now, I carried out research on geothermal energy, specifically looking at how to optimize production from enhanced geothermal systems. And before then, I worked in the oil and gas industry for 13 years. So I've seen a lot of opportunities for the transfer of technology from the oil and gas industry towards enhanced geothermal systems. And the objective of this panel is for us to see how we're going to pivot, right? Enhanced geothermal systems, here we're looking at systems where we're going to inject a cold fluid, usually water, into rocks that have been enhanced. They are at high temperature. We try to extract the heat from this rock and produce from them. And there's been a lot going on in the past decade. And we have a lineup of panelists that are going to help us understand what's been going on in the past decade, what are the challenges, technical challenges, what the risks are, and how we could take learnings from the oil and gas industry, transfer technologies, methodologies to try to reduce risk, to reduce cost as well. And in the next few minutes, the panelists will be coming up to introduce themselves. But I can assure you that we have panelists that will do justice to the concept of where we could go with EGS in the future. So just sit back, relax, and listen to the panelists. I'm going to start with Dr. Mark McClure to introduce himself, what he's been into, and where his interest lies in terms of EGS and geothermal technologies.
Well, thank you, Rita, and I'm really excited to be here today. I'm the CEO of ResFrac Corporation. We make software that integrates hydraulic stimulation modeling with reservoir simulation. We also do consulting services. Most of our business is actually oil and gas. We work with the healthy majority of the top 20 oil and gas producing companies in the US and Canada. But we also work with several of the leading geothermal companies, especially focused on EGS. Prior to starting this company, I was an assistant professor at the University of Texas at Austin in petroleum and geosystems engineering. And before that, did a PhD at Stanford. Rita and I had the same advisor role in Horn and specialized in EGS for that work. So I've done a lot of academic work on EGS over the years.
All right, thank you. Dr. Albert Jonter.
Yes, thank you, Rita. So, hello from France, from Europe. So I am Albert Jonter. I'm deputy manager of a company named ES Geothermy. ES means Electricity of Strasbourg, because I am in eastern part of France. And I have strong background, I would say, in deep geothermal energy, working first for the French Geological Survey, the equivalent of USGS. And now I work for industry. So I'm deeply involved, I would say, in a research project. I'm a scientist working for industry, and I work a lot on EGS. I'm coordinating a European project about EGS. And in our company, we are exploiting two geothermal plants EGS plant. One is quite famous, it's a sulfur power plant, and the second one is the new one, which is a return heat plant. We are producing heat from fractured granite, and we stimulate those wells. So we have two GS plants we are exploiting now for 5 years. And with our team also, we are working on new projects about exploration and doing new projects. And I'm happy to be in the panel today.
Thank you, Albert. Ron Dusterhoff.
Thank you, Rita. My name is Ron Dusterhoff. We're very honored to be here today. I'm a technology fellow with Halliburton, and we're involved in all aspects of the energy industry. My background, I've worked here 37 years. I've been all over the world, started off conventional oil and gas, went into deep water, then unconventionals, including coal bed methane, heavy oil and shale. So a lot of our focus these days is in thermal recovery of heavy oil. And I see a lot of parallels that we can run across here. I think from the geothermal perspective, I think it's going to require integration of both core technologies as well as fringe technologies. So, you know, we can look at drilling, stimulation, reservoir completions, and those are core technologies. But as we start looking at some of the thermal modeling and then continuous thermal monitoring of these reservoirs to get better thermal recovery, those are going to be some of the key things that I see going forward. With that, I'm looking forward to the rest of the session. Thank you very much.
Thank you. Tony Pink.
Yeah, good morning, everyone, and thanks, Rita, for my pleasure to be here today. My background is 30 years in oil and gas. I am a geologist by degree, and really I've spent the last 30 years trying to sort of break rock as fast and efficiently as possible, and doing things with cutter technology and drill bits, automated applications, and really trying to make some big jumps in performance. And you know, I really see the opportunity here in geothermal, in EGS and closed loop, that if we can knock down the drilling costs significantly and get the development of these wells down by, you know, I think halving the well cost is well within our capability. I think we really open up the economics of this worldwide, you know, combining that low cost well creation with decent rock, with decent heat in it. I think there's a real opportunity for us all. So yeah, excited to be here this morning.
Fantastic. Thank you, Tony Pink. Lauren Boyd.
Hello, everyone. Apologies that I'm not with you on video, but my name is Lauren Boyd. I am the Enhanced Geothermal Systems Program Manager at the U.S. Department of Energy's Geothermal Technologies Office. And I've been with the Department of Energy for around 12 years, working in the EGS space for the majority of that time. And under my portfolio is the Forge project, which hopefully we'll touch a little bit on, but there's a session on later today. But excited to be here. I think this is just such an exciting time for geothermal. You know, this incredibly, it's a really neat opportunity to be able to communicate with the oil and gas sector and with so many folks out there that are interested in geothermal and talk about the opportunities from this baseload, flexible, renewable energy source that that we can all sort of work together to advance. So thanks for inviting me. I'm privileged to be on this panel with so many esteemed folks and appreciate the opportunity to talk about what I know about EGS.
You're welcome, Lauren. Okay, so I have a couple of questions in mind for the panelists. And Albert, I'll start with you. So EGS, Enhanced Geothermal Systems, or Engineered Geothermal Systems, as we call it, it has evolved from the 1970s when the project started at Fenton Hill. And we can imagine that in the past decade, there's been a lot of things going on in the EGS space. So if you could just tell us what's been going on with EGS, what has worked, what hasn't worked, what has been, you know, what's just been going on in the past few years.
Yes, thank you, Rita. So effectively, you know, I will give the view from Europe. So you're right to mention fentanyl, which was a pioneer project. And in Europe, in fact, a lot of achievement have been done. So for instance, many operational plants, EGS plants, are now operating over the last decade. So in France and Germany. So there are many real and tangible results because we are selling energy, we are selling electricity, or we are selling heat. So when we start those, I would say, operational projects, we did a lot of R&D in the past, and we have a common project. We have a French, German, plus US, plus Japan, many countries contribute, and we have a European project, and we learn that. And we did mistakes, and we learn. We learn by doing. And what we learn, that it's very difficult to create a heat exchanger from scratch. And by drilling, what we find natural water, even at great depths, in a granite basement, which is reputed tight rocks. And in fact, there is water, very saline water. But the problem is, as you mentioned, is to engineer, is to connect the wells to the natural fracture in which we have water which is circulating. So we learned that it's a mistake to drill vertically a well in a vertical fracture system. It's better to do, for instance, incline well. It's some lesson we learned. We learned also that at the top basement, we have much water than at great depths. So it's not necessary to drill at 5 kilometers deep, as we did in Souls. In Rittershofen, from the second plant we drill at less than 3 kilometers deep. So many things like that, how to drill, the depths of the drilling, because EGS, we cannot increase the temperature, but you can increase the flow rate. And then we try to increase the flow rate and to find method to increase this kind of energy for producing either heat or either electricity.
Thank you. Lauren, would you like to give us some perspective outside of Europe, something you've been involved with?
Sure, Rita. Yes. So I think that Albert touched on so many critically important things, and obviously as someone who's been involved in the longest running EGS project, he has quite a background here. I think that something that we've seen in the United States that's very relevant and crosses over are some R&D advances that are critical. So from the demonstration standpoint, I couldn't agree more. There's operational plants that many people don't realize in Europe. There are a few in the United States as well from a near field perspective, which I can talk about in more detail later. But from an R&D perspective, which is what I do at Department of Energy, there have been some advances that are really critical in moving EGS forward. So I think, we have a lot of modeling experts here on the phone that can talk about this in more detail, but I think that advances in the modeling space and computational techniques and capabilities have really led us to be able to model and analyze more complex reservoir simulations, taking into account things that we weren't able to do before, multiple fracture propagations and interactions. And so being able to actually model the hydrothermal, mechanical, and chemical behaviors of fracture networks has really helped us to better design stimulations and better design EGS. I think also reservoir geomechanics, which is tied to the modeling, but this is something that back in Fenton Hill we recognized was obviously important, but I think it's become a much more critical topic of consideration in terms of working very hard to assess in situ stresses prior to any sort of field development, looking at the role of natural versus induced fractures, which I know folks on this panel have a lot to say about as well, and then how those things interact and actually inform how you build your well, aligning your wells across fracture sets that might actually allow you to build more complex fracture networks and reservoirs. And then multi-stage stimulation. This was not a concept that when I first started at DOE that we were necessarily recognizing and talking about as critical as it is. And so a couple of projects back in the early stages of my time at DOE were looking at chemical diverters. I can talk about that a little bit later. But the criticality of multi-stage stimulation and the implications for preventing thermal breakthrough and preventing permeable pathways that allow thermal breakthrough is really important. And then finally, seismicity. Albert can speak to this as well, but we've really improved our understanding of seismicity, not only for mitigating hazards, but I think also for using it as a reservoir characterization tool, which is critical for designing EGS that are efficient and and long-lived.
Okay, thank you, Lauren. I think this is very interesting to see this perspective also from what's being done in the United States. Ron, so I know when you were introducing yourself, you talked about things in terms of thermal recovery, and I can understand that there are some parallels between thermal recovery in the oil and gas industry as well as in EGS. Would you like to touch on some of the things you see and how it has evolved in the past decade and how it might just help with our understanding of enhanced geothermal systems, EGS?
Happy to, Rita. You look at the SAG-D, which is the steam-assisted gravity drainage that's happening in the heavy oil in Canada. One of the things that you have is a steam injection well and then a oil producing well. And getting good steam distribution over a long horizontal interval has been a challenge. And one of the things that's really helped us is long-term monitoring with fiber optic at these very high temperatures. We're monitoring continuous at 230 degrees C for years at this point now. So it gives us a little bit of a snapshot of how well we're distributing the steam. And as a result of that work, in the past probably 10 years or so, we've been working on flow control devices for thermal operations. And that technology is really just starting to take off this year in Canada, where we have a number of flow control valves and we're able to monitor the efficiency of that with steam. So I see a good parallel there for our injection wells with geothermal, that we can actually not be robbed by one natural fracture, but distribute the flow through many natural fractures and get better thermal recovery. So I think there's a huge opportunity there. Also feel that Mark needs good data to calibrate his models. And with good data, he can do a better job with his models. So I think that's important.
Yeah, so now that you've mentioned Mark, Mark, I don't know if you could just throw some light as to, what you've seen in terms of your research, in terms of your modeling, and how we could gain experience from the recent EGS projects that are on ground.
Yeah, I am really bullish on the application of multi-stage hydraulic stimulation. The holy grail of EGS for decades has been to generate a huge amount of fracture surface area, because you can get a higher flow rate, and you can get that high flow rate for a long time if you have a lot of different flowing pathways. And that's exactly what multi-stage stimulation with limited entry completion accomplishes. In recent years, companies have cored through hydraulically stimulated regions in shale and excavate the rock from the ground and find thousands of conductive fractures in the rock. So this is something that's done routinely all the time in shale. And the idea that we're finally looking at taking those insights and applying them in geothermal, I think is really exciting. There's a tendency for fluid to take the path of least resistance and kind of flow into dominant flow pathways. But when you do mechanical isolation in multi-stages and then you use limited entry completion, you defeat that and you force flow to flow into a really distributed network. So that's a really exciting concept. And 10 years ago, that was not on anybody's radar screen. I would talk to people about it at conferences and they'd tell you, that's crazy. And it was not on the map. And that's totally shifted in the past decade. I actually think that the DOE has been a big part of that. When the DOE started the Forge project and at the outset talked about multi-stage stimulation, I think that's what suddenly got everybody's attention on the topic. I think that's been a huge role there. So that's from the modeling perspective, we need a lot of fractures, and that's how to do it.
Thank you very much. Thank you. Tony, what would you have to say in terms of where we are at in terms of the EGS projects? What can we gain from where we are now?
I think it's really interesting to see the broad range of expertise in different parts of EGS well that we have on this panel today. My analysis is really looking at how much time we have taken to be able to deliver the well for these people to go about their business and create that fracture network. So what I've seen over the last 10 years and what has really changed in the last year is, the geothermal industry has remained relatively low tech, and I don't think the oil and gas should be arrogant or, brazen about, technology transfer to the geothermal industry. But the careful application of technology in certain places in geothermal can have a significant increase in a significant reduction in well costs. Yeah. So in the last year, I've seen this real openness coming to looking at, applying things like PDC cutters in granite. This would have been an area where we would have just completely avoided. We would have just thought that a very expensive bit would have been destroyed in hours potentially. Yeah. So that realm and that technology of diamond technology being applied to hard rock is really, there's an opportunity moving forward. The other areas really that I think is in good automation and good algorithms for controlling the dynamic environment that we have in these wells. Yeah. And if we can get much more energy in a very stable well way down to the cutting structure, I think we have that ability to start failing these harder rocks in a faster and efficient way. And they're also out on the fringes. There's some small companies that are doing some really amazing new technology in the realm of plasma and in particles. Yeah. So firing steel shot at the rock and then seeing how the rock fails. So it's really nice to see in the last 2 years as the focus in geothermal start to really absorb in a lot of new technology. Yeah.
Oh, great. Fantastic. So one of the things that comes to mind is, there are a lot of challenges with enhanced geothermal systems. It's been on for many years. We aren't yet at the stage where we say it's commercialized. So if the panelists could share with us what are the primary challenges that they see, and what is the cost implication? If you could just tie these challenges to the cost implications. Mark, let's start with you on that, and we'll just go through the panel.
Sure, you need a whole lot of hot water and steam for a long time. That's what you need. And so, flow rate is challenge number one. And you just need to get, hot water is not as valuable as oil. And so you need huge flow rates to make this work. That's point number one. And so to do that, I think we can look at, I think what they've done at Salts is they've targeted really large conductive fault pathways. And Albert can correct me if I'm wrong. But they've been able to find, really conductive natural fractures and natural fractures that were really conducive to being stimulated. Another approach that I was referring to is to creating just a very large number of fractures. Using oil and gas techniques, and that way, if you have a whole bunch of kind of conductive fractures, they add up to being something that's really conductive. But one way or another, we need a huge flow rate. We just need a ton of water circulating through the ground, and you can't emphasize that enough. Everything is expensive. The power plant costs money, the well costs money, the operation. You just have to have a huge flow rate. And then second, Ron referred to this. It's flow conformance. So if you have a huge number of flowing pathways, you have a huge flow rate, but then fluid starts kind of concentrating into a few pathways. You cool down the rock around those pathways. Pretty soon you start producing cool water, and now you've lost the value of the system. So I think that is a very important area of future research. I think it's an engineering problem that we can solve. There's no law of physics that says we can't do this, but like Ron was referring to, some of these flow conformance, flow valves ideas, if you do a cased and cemented well, you could just go in there and do a cement squeeze into a zone. There's a lot of different possibilities. Monitoring with a fiber to see where the short circuit might be happening. All of these are going to be critical. And so I think flow rate and then keeping it hot is key. And then on the other side, the cost side, I think there's huge opportunity to keep bringing down cost on drilling. NOV is a part of that. The Forge project, for example, has drilled their wells extremely fast, really kind of record setting. And so bringing down cost of drilling and then bringing up revenue per well.
Oh, great. Yes. Revenue up, drilling down. Lauren.
Yeah, I can weigh in on that. Absolutely. And if I could just touch on one of the comments, I would argue that depending on the way that you define EGS EGS is commercial now. Albert spoke about that at the outset, and there are a number of projects in Germany and France that are commercially operating right now. Thinking about EGS as this, I think that Colin Williams defined it this way in 2008, 2011 in one of his papers, but this idea of wherever you are seeing a measurable increase in production over your natural state because of a mechanical, a thermal, or a chemical stimulation, that's EGS. And so if you are stimulating a well that is underperforming, has low injectivity in the margins of an existing field, inside an existing field, or if you're doing that in a greenfield environment where there's no geothermal development whatsoever, at least at the Department of Energy, we consider both of those enhanced geothermal systems. And I would argue that there are operational EGS that are on the margins and within hydrothermal fields in the US that are currently working. And there are many in greenfield environments and near field environments in Europe. So I want to put that out there. That is not to say that there are not challenges that remain for widespread and commercial deployment of EGS. And I think Mark touched on beautifully sort of everything that I would say in terms of the technical challenges. But I did want to mention that there are a few, even in the US, there's a few projects where we've seen, on the order of 2 to 6 or so megawatts just from small projects. But then in terms of the technical challenges, I guess I would say, reiterating Mark's comments, that stimulation planning and design, like how do we design and optimally stimulate a well and that honors the in situ conditions. And so we talked a little bit about the recognition of the criticality of these conditions. So rolled into that is the equipment that actually works, because we don't currently have that. I would say, is on phone calls multiple times a week with our Forge team, we haven't had one packer that actually worked. We need to be able to drill deviated wells, horizontal wells. We need to be able to run a CBL in a well and understand what our cement job looks like, perforate. But most importantly, most of that is possible. Most importantly, we need to be able to isolate zones, as Mark communicated and Ron, and we need to consistently and effectively stimulate those zones, because that is the most critical aspect of moving EGS forward. And then we need to, develop better models. Therefore, we need better data. So tracking data in the subsurface in these harsh conditions is really important. And then understanding how different methods can actually help us create different EGS reservoirs in the variety of EGS conditions that exist. No geothermal environments are the same from a geologic or a stress perspective. And I think that positions us differently than the other renewable technologies, because we don't necessarily have an easy resource to assess. So I think that those are some really critical research areas. And then of course, the fracture subsurface control, being able to track the evolution of our reservoirs and then in real time change how our reservoirs are evolving over time. So I'll leave it there. I know other folks might want to weigh in.
Okay. So Albert, I don't know if you would like to, weigh in on that as well. Give your own perspective of what you see as the primary technical challenge and what's being done to, try to work on it, how we could manage the cost if it results in some cost problems for us.
So maybe, yes, I would like to at least to speak about 2 topics. The first one, it was mentioned by Tony, it's about drilling. It's clear that innovation in drilling costs is probably, at least in Europe, one of the most costly part of a project. So between 40 and 50%. So if we can, I would say, increase the ROP, the rate of penetration, so drill faster, we can decrease the cost of a given project. So we need to improve the drilling technology. But what we observe, we have no problem to drill granite, which is hard works. It was easy. The problem we have 6 very thick sedimentary layer, which is very heterogeneous: sands, clay, marls, different kind of rocks, limestone. And sometimes we have more issue to drill this part than to drill the basement, which is generally easy to drill and then to get a high ROP value. So it's clear that we need to, if we need to have more EGS commercial project, we need to show that we are able to decrease the cost of drilling, and then we will attract more investors. So today, even from the past, but even today, is still very expensive. The second topic, which is important in terms of cost, and you also mentioned by Lauren and Mark, it's about also, I would say, to design and to apply some, I would say, complex stimulation strategy, thermal, chemical, hydraulics, how you are doing it with packer, no packer. We test many technology with coil tubing as well. We inject some chemicals to dissolve some minerals to improve also the permeability at well scale, very in the near well zone. So also this part, you need to know your well very well to have a lot of information about your well. And you also mentioned by Tony, I think we are much less information than probably in oil industry, because geothermal, we have less money. So generally, investors, they put less money to characterize the wells, to know better the wells. But I think we have some opportunity to improve this transfer. And the last things we did very recently to improve, I would say, and to have some technical challenge, because we have big sediments and we have big faults in the sediment, we did a 3D seismic survey, which was the first time in our area we conduct such a survey, which is 200 square kilometer, large survey. And the idea was to map the fault even in the sediment. We cannot see the fault in the basement. There is no horizon, but at least we can propagate and see where is going our fault to drill, I would say, smart wells and incline well. And so we did that, and we are working on that. So we come from, I would say, oil industry. So to try to transfer, the first time we did that, to transfer this method, 3D seismic survey, to our field, because we have large faults and we want to know their geometry very well. And then we spend some money to do that. And in order to better, I would say, target the wells in the future.
Thank you very much. So I'm going to take a few questions from the audience. And Albert, since I have you here, let me start with you. So yesterday there was a panel talking about geothermal and social license. So will the use of fracturing, stimulation of these reservoirs, hot geothermals social license, the EGS social license, and what's your view on this issue of people having opposition to fracturing and stimulation?
Yes, thanks, Frida. It's clear that we are, I would say, a kind of good example or good bad example, if I would say like that, that some months ago, one of our competitors in the eastern part of France, they drilled 2 wells at 5 kilometers deep, and they did some operation, hydraulic tests and things like that, and they generate induced seismicity, which was felt by the local population. Wow. And Strasbourg is an urban area, and we got several earthquakes felt by the population, and now the population are against the geothermals. And so it's a very big challenge because of that. Now the mining authorities, they asked to stop all the projects in our area. So, and several expert committees are evaluating what has been done, try to understand what has been done, but people felt several earthquakes. Magnitude was roughly, the maximum magnitude was roughly 3.6. And it's, I would say, for us, it's very critical because we cannot develop new project. We have a project which is located 10 kilometers from this site. We drill the first well, and now we are not authorized to drill the second well, for instance, where they blocked our project, and we have to wait maybe 1 year, the feedback from the expert committee to give us some maybe new regulation. But it's clear that people now, they know about geothermal, but they know the bad side of geothermal, which is induced earthquake. And there were more than 2,000 people claim about to get money because they have some structural damage in their houses. So it's clear that in the area of Strasbourg, which is urban part, it will be very difficult to do project probably in the next years. And maybe we can do project, but more in the countryside. But it's very, very difficult today.
So, Mark, I know you've been doing some modeling on, hydraulic fracture stimulation. Would you know if there are ways this can be reduced? Is there, anything from your studies that you could share with us? because this is an issue, and if EGS has to get to the stage of being commercialized, it has to be acceptable by people. I don't know if you want to share something.
I think that the best document I've seen is there's a DOE-sponsored induced seismicity protocol. Ernie Major is the first author on it. They did an excellent job of going through a process of evaluating the local geologic settings, going through an entire process of understanding, what is the seismic hazard, how does that relate to seismic risk, and I really think it's a gold standard process, and I think that it's the kind of thing where if you follow the right procedures, then this is absolutely a manageable issue. I do think location matters, right?
Mm-hmm.
It doesn't. It's a lot tougher right underneath the city than it is out in the countryside, like Albert said. So, I don't know that we'll ever bring earthquake rate to zero.
Mm-hmm.
In fact, if you look at the geysers in Koso, those are seismically active areas, and they've been that way for decades, and it's not an issue. I think what's really important is to just be really transparent with the public, reach out to people, make sure people understand what is possible, and then a magnitude 3 earthquake, is really not damaging. It's something that if people know could happen at some point someday, maybe then it's manageable. Just important to be transparent. But no, I don't think we can bring it to zero. And I do think it's an issue of geologic setting. So I will make one note. One approach to EGS has been to target large faults because they're really conductive, but they also may be more likely to host seismicity. So an opposite perspective would be to avoid completely, do that 3D seismic and completely avoid anything that looks like a fault, and then rely on like a multi-stage stimulation approach. It's a very different philosophy. What they've done, in the Sultan region has been very successful, but a completely different philosophy could be to avoid faults entirely. And I think that would also have a big role in reducing seismic hazard.
Oh, wow. This is very interesting. Very interesting. I want to take another question from the audience. Tony, I'm going to send this to you. They're talking about, do we have standards for high temperature electronics at this high temperatures, 200 degrees C, 300 degrees C? And, what can be done really?
Very, very, very good question. Yeah. So, if you say some of the biggest challenges, so the two biggest challenges of drilling these wells is one, breaking the very hard rock. The second one is knowing where you are. Yeah. And knowing where you are from if you want to develop a horizontal borehole, and two horizontal boreholes side by side, so that you can then have relatively short distance between those two wells to fracture between them, and maybe that reduces the seismicity. You really need to know where you are. So today, the gold standard is about 175 C. The extreme standard is around about 200. Above 200 degrees C, there is no current commercially sort of economically viable electronics. We've been working in NOV a little bit with the National Renewable Energy Lab, NREL, in Denver, and we're looking at electronics for up to 400 degrees centigrade, built on a gallium oxide platform. But the challenge with that, to get the chipset, the modems, all the electronics you need to be able to transmit signal, you're looking at 5, maybe 10 years away. So an alternative way of thinking about this is, so how could we insulate tools? Yeah. So we could say you have 175 degrees C tools, but you insulate them. Okay. And then, where I'm thinking is really maybe we have to start thinking of it as a total system. And if you think of it as a total system, how can we put cold fluid in at the surface, transfer that fluid fast at high volume down, retaining its temperature? How can we insulate the drill pipe to minimize the loss of heat, the increase in heat as that cold fluid transfers down? How do we have continuous circulation so we don't have static thing? So I think in the near term, to solve this problem, the most likely way is a system approach of a combination of things, of cooling the mud on the surface, getting it down there as fast as we can, insulating the pipe, putting the electronics in a thermos, or combining it with Peltier plates so we can remove heat, and think about it as a system so that we can do stuff in the next 2 or 3 years while we continue the leading edge R&D out on the fringes in the 400 degree C area. So I think we do both simultaneously, and hopefully, you know, we can start drilling some very challenging wells, know where we're at with a kind of hybrid approach.
Great. Ron, would you like to weigh in on that? You know, you've had some experience with, you know, heavy oils, and, you know, how we do in terms of electronics for.
Yeah, I agree with Tony on the electronics. It's a challenging issue you have with high temperature electronics. You can do things like mud cooling and trying to keep the electronics from getting too hot during the drilling process. You know, so that's a key area that we focus on. We're trying to get the electronics functioning at higher temperatures for drilling applications. Well, hopefully we'll get there. You know, that's going to be time, and it's going to take some new technology on the electronics to get there. On the monitoring side, we've gone away from electronics. You know, the fiber optic has been our area of preferred monitoring for both temperature, acoustic, and now pressure. This gives us the ability to function at, you know, 230 degrees for continuous operations. The highest temperature that we've monitored to date using a nitrogen blanket to prevent oxidation is about 342 degrees Celsius for a matter of a few hours. So we're able to monitor very high temperatures for a short time and then high temperatures for a long period of time. This technology is improving. You know, it's kind of like you go to the development of where you're happy. In heavy oil, we're pretty happy at 230 degrees. If we go into geothermal, we have some technologies that could expand it, but it's going to require us to look at that and understand what the conditions are. So that's going to be a key area, I think, for us.
Great, thank you. Lauren, I don't know if you've you know, had this direct relationship with project costs, like in the projects you've been involved with. If you could just tell us how the cost is, and, you know, how you think we could try to reduce the cost of EGS.
Absolutely, sure. So the costs in terms of the modeling that we do at the Department of Energy in collaboration with the National Renewable Energy Lab indicates that basically cheaper drilling, basically lower cost per well, fewer wells, which you can get to via zonal isolation, and then lower financing costs are actually really critical drivers for moving EGS forward. And so inherent in that is not only increasing your ROP, so we talked about that, some of the really significant advances happening right now at our Forge project in Milford, Utah. There's a whole session at 4:30 about this today. But there's also another significant portion of the costs associated with drilling that are associated just with the well construction. So casing and cementing costs are dramatic, 30 to 50% of costs in general in this area, where there's a lot of room for improvement there. And I think it's something that our communities could easily tackle together and find ways to minimize these costs, considering the implications. And then again, using fewer wells, but maximizing the use of wells by zonal isolation. So as Mark said, creating these large fracture networks that can flow a lot, that's what we need a lot of water, is really, really impactful. The other piece that is something we're recently sort of investigating a little further is the ability to scale up. And so it kind of touches on this fewer wells idea. If you can get more from fewer wells, but you can have a lot of wells, and we can increase our plant size. So thinking when we model this, we model by plant size, but if we can make our operations on the order of 100 megawatts as opposed to 10 megawatts, we are maximizing the use of our infrastructure, reducing the significant costs associated with pad drilling, with developing pads, with all of the other accoutrements that go along with operations. So scale up is really critically important too. And reducing that risk by getting better at drilling, more efficient at drilling, and maximizing what we're doing in each well, so we have to drill less. Those are really the biggest cost drivers right now. In terms of actual numbers, I can go into that if folks want, or I can point you towards some documents that show those. But I don't want to take too much time on the numbers if other people have comments.
Yeah, so you talked about scaling up, and I have a question from the audience that I would just like to know if we could actually move from megawatts to gigawatts. And any of the panelists could just take this one, what their thoughts are on scaling up, to much larger scales for EGS.
Yeah, I'm happy to weigh in on this, Rita. I think that that's where we need to go. And I think that we, with some technology improvements, that we can get there, especially some of the technologies that Mark alluded to that are utilized in the oil and gas industry. If we're thinking about multi-zone stimulation on the order of long horizontal wells or near horizontal wells, and fracturing in 30, 50 zones per wellbore with multiple wells, I think we can get there. And this is an ingenious industry. We are creative, really smart folks, and in geothermal and in oil and gas. And I think if we can do it in shale, we can do it in granitoid rocks. And I think that is critical. Another way to get there in faster is to work in super hot environments. So you can obviously get more output from your well if you drill in an environment that's 700 degrees, but keeping in mind the electronics discussion we just had, that's much more challenging from an operational standpoint, from a monitoring standpoint. So that's my thought. And from the electronics piece, I would just say that DOE has had a long history of work in the high temperature electronics space, from working with Sandia National Labs, GE, other entities. But the challenge is definitely getting over that 300 C mark, and then also having a market to deploy them, because we do have some functional components, but we don't necessarily have anywhere to put them.
Yeah, and supporting what Lauren says there, one of the challenges, chip manufacturers, the business model for them is volume. So say if we come up with a high temperature chip in the geothermal industry, we're going to need 300 of them, 3,000 of them, 30,000, but we're not going to need 3 million of them. So then it makes those chips extremely expensive, and the tooling very, very expensive, because there's not the volume that comes associated with electronics in general. Yeah.
Exactly.
And maybe I can add something that we can, if we want to scale up also, we can also try to have more revenues. For instance, in our case, because we are exploiting brines, they are very rich in lithium, close to 200 milligrams per liter. And if I take the example of our plants, which is a Certofan with 300 cubic meters per hour, we can produce, if we are able to do that, we can produce roughly 2,000 tons of lithium carbonate equivalent per year. And at roughly at $10,000 or euro per ton, it's a very important revenue. So we need to be clever, not only to produce electricity, because in France we are a nuclear country, but we can produce lithium, maybe heat for industry, heat for local people. So if you have producing heat, you generate local job, for instance, greenhouse, and then you have strong support for politicians and people. If you are producing electricity, in our case, it's going on the grid and nobody can see it. But if you have a great job, local job with your local plants, it's also very beneficial. And then you have the support of the people. So I think we need to be clever and to get more revenue. And maybe the last idea we are doing in a research project I'm coordinating, the name is MEET, we try to re-inject at lower temperature. Today, we are pumping roughly at 170 degrees C, and we are injecting at 70 degrees centigrade. But we can re-inject at lower temperature. And then we are doing some tests by adding mobile ORC unit to try to do more electricity. With the same wells, the same infrastructure, you can produce some more kilowatts, and then you produce more with the same structure. So there are some way to also improve the economy, to try to produce, to co-produce with metals, with heat, and also to extract more the thermal spectrum by producing, for instance, more electricity.
And Rita, if I could just build off of Albert's point, which I think is just a fantastic one that we don't talk about enough, the opportunity not only for improving the economics with other value streams, but also improving our production, as you said, from efficiency, but from hybridization. So hybridizing with CSP, hybridizing with solar thermal, these opportunities for more flexibility, more power, load following capabilities, which is important in the US, there's a really exciting opportunity that we haven't really even begun to study the impacts for EGS in those areas that are very unique. So Albert, thanks for that great point.
Yeah, and I think adding to that is the, the environmental footprint. As solar becomes prolific and people are using greenfield land for solar, it's really interesting that all of the sort of footprint we create, seismicity aside, is subsurface. Or a large part of that is subsurface. So a relatively large network of wells can be completely invisible to the population with a relatively small facility on the surface, which you then tie into using in greenhouses and other things. I think it's very green, yeah, and that's what I like about doing the sort of EGS model of getting a lot out of it subsurface. Yeah.
I might interject one thing here too. We were talking yesterday in one of the sessions about risk and really the inability to really fully understand the risk. A lot of people undersizing topside facilities just to avoid spending too much and then kind of working in a pilot to understand and then building up. I think that we need to get to the stage if we want to really be commercial here. I kind of view us as at a pilot stage right now. To get commercial, we need to be 10, 20 times what we're doing right now. And that's going to require us to have better models that are de-risked, that are calibrated so that when we start going into these larger scale projects that we know what we're going to get and we get what we expect. I think that's going to be critical.
I'll also note on the commerciality, a lot of the edges of existing conventional geothermal fields, wells are drilled that are not permeable enough to be economic. So these are places where we have high temperature at shallow depth and there's already complete surface infrastructure. Often power plants are built for conventional geothermal fields and then they're not getting enough steam to operate at capacity. So there's, in the short term, as we're starting the beginning of this whole thing, targeting places like that is very advantageous and can dramatically improve the cost in the short term as we move up the learning curve.
Rita, can I add to that as well? Is that all right?
Oh, okay, go ahead.
Sure. Well, I just wanted to point to build on Mark's point that this opportunity to work in a near field environment gives us the opportunity, to Ron's point, to reduce our risk by learning by doing. And we have not had that opportunity in the geothermal industry. The oil and gas industry clearly has for decades. And when you compare the lack of ability to learn by doing, plus the very, very significant difference in public spending on oil and gas, $9+ billion for fossil energy versus $1 billion since 2004. This is from Breakthrough Energy statistics. That's a very big difference in research and development and the opportunity to learn and to tweak and to try again and to hypothesis test. So I think that there's an opportunity in the near field environment to learn and to grow and test out some of these technologies, but in general, just to reduce risk in general, to make it more palatable. Thank you for letting me jump in.
No problem. You're welcome. I wanted to ask a question with regards to the barriers to EGS being technologically ready and commercially viable. But I see that like even most of the audience are interested in knowing stimulation, fracking, the reputation. They feel that the reputation is a barrier. And how can we repair the reputation from the incidents that had happened in the past to prevent, to enable us move forward with EGS?
So maybe I could start. So one thing which is the easiest to do, if for instance what we are doing in our area is we organize visits. We show to the people a plant, how it works. You show also people. So we are expert discussion with local people. So we explain how it works, geothermal energy, what is stimulation, even it's complex because fracking, it's not politically correct to say that, at least in Europe. So we need to explain and to show. And if you show by doing real things, not even you have a very nice website, movie, slide, or a very nice publication, people, they don't read that. You need to show them some things. And when people are against, we observe that when people are against geothermal, if you're going on site, you are showing how it works, you explain how it works, and then at the end they say, okay, I understand better, and do new project. And I think the best thing is to organize visits and then to convince whatever the people. It could be politician, it could be association, it could be various stakeholders, and also pupils and students. And it's the best way, I think, to show I would say tangible realization, and then it could work. So I'm optimistic by try to show that we can do better. And for instance, we have 2 plants operating for the last 5 years, and nobody felt any earthquake. It works. Geothermal energy, EGS work even in fractured rocks, even in granite. We have no problem. So you need to show that and to say that to people. Good, show successful project and and good realization.
Yeah, I think supporting what, ignorance and lack of education about it is really harmful. Yeah, we need to learn the lessons that the nuclear industry, felt in this area. Me personally, I did what Albert said. I was shown around a nuclear power station in UK when I was about 16, 17. And it took away the fear from me completely, and I had a totally different opinion on nuclear energy because that fear had gone away when I saw the inside of how a plant worked and how many safety systems and everything were there. It gave me a totally different perspective. I think we have to work on our PR as an industry from the get-go, yeah. And I think it's really important that we do that. So this fear of microseismic events is really not necessarily well founded on science and help our industry get off to a good start. So I think we have to think about the PR part right away. Yeah.
I think also, Tony, to add to that, just what Mark referenced earlier, the protocol that we follow in the United States, but there is also a lot of work going on in Europe for real-time seismic monitoring and mitigation. I think that education is critical, but there's also the side on the operators to make sure that we are really doing our homework in advance to assess stress conditions, assess the geology, understand where faults are, actually look at probabilistic seismic hazard assessments to see what could happen before. So we have to educate, we have to make sure that our the folks that we're, the stakeholders that we're working with understand what we're doing and feel comfortable, but then we also have to make sure we're proving to them that we're working safely and we're working smart. So I think, and establishing these international protocols is a really critical piece to that.
Yeah, I will add to that a little bit, maybe really briefly. Monitoring seismicity is important long-term. Also during the jobs, microseismicity, we can get a good idea of how we're disrupting the rock and how we're disturbing things, and that can allow us to avoid ourselves getting into problems with stress interference and building up stresses that will ultimately be released in a bigger event. So I think there's a lot of things we can do. A lot of it's around education. People need to understand the subject better and clearer and understand the risks. One of the key things that was brought out earlier, if you look at solar and wind, the amount of stuff that we see on the surface is huge. What we're doing here is we're actually working in the subsurface. We're not disrupting the surface, and we're I think we got maybe a bad reputation in the oil industry, but when you look at the amount of work that's been done, we've done it very well and effectively. I think we need to communicate that better.
Great.
And I think as the industry develops beyond the pilot stage for EGS, I think, robust regulatory attention is going to be critical. There's a lot of things that people do that can be dangerous or environmentally damaging if they're done improperly, and they can be done safely if they're done properly. And I think the whole industry will benefit if there's robust regulation to make sure everybody's playing by the rules and doing things the right way.
Okay, so we would also like to know, EGS uses water, right, primarily. what's the future if, you know, there's water scarcity, and what alternatives could we have to, you know, help us to gain more, extract more heat from enhanced geothermal systems, you know, just improve the process in general, you know, like more revenue, like Mark said. So let's talk a little bit about what scarcity of water, alternative working fluids in EGS. Mark, you want to say something? Or Ron?
I may jump in real quick there. Just, you know, we were looking really closely at using CO2 as a working fluid in certain cases, and actually taking CO2 sequestration projects and then, you know, harvesting geothermal energy from them is a way to get another source of energy and revenue from these kind of operations. So I think there's a huge opportunity there to look at CO2 as a working fluid as well as steam.
Great. But you want to say something?
In our case, we try to improve the efficiency of the, for instance, of the surface installation to produce more with the same system, as I mentioned, with the mobile ORC, to also better monitor also with fiber optic. So to add some technology to better know our system and then to improve our system. So we never try CO2, I would say, injection or thing like that. But also what I already mentioned. So one thing was also to extract also some metals, lithium, but we have also other kind of metals. So we can maybe imagine that in the future, we are able also to recover other minerals from the brine we are exploiting, for instance, and we could add some revenue. But it means we need also to add some, I would say, modules to the plant. But so I see some, I would say, improvement in that direction.
I would also add that in some analysis that we did in our GeoVision study, which is from 2019, looking across the power sector at water use, when we analyzed geothermal contributing around 60 gigawatts or 8.5% of national generation by 2050, we found that for the electricity sector, we're only actually using 1.1% of power sector water use. So it's actually relatively low comparatively if you take into account system water use. And I think something to point to from one of our old demonstration projects back from 2009 to 10 was at the geysers, in the Northwest geysers, we were using treated effluent water in Lake County. That was not going to be utilized for anything else. The Forge project is currently, or at least at a couple of points in the project, are using water that's not usable by any agricultural communities nearby because of high solids. So there are opportunities for different streams to be used and relatively low impact water-wise, even with high penetration rates. So of course, there's the other opportunities like CO2 and other working fluids, but I think even from a water perspective, it's really a minimal impact.
Fantastic and very interesting. So for all of you panelists, I want you to just take a moment to think of what technologies, methodologies can we just bring from the oil and gas industry that we haven't yet used in EGS that could make an impact in reducing cost or improving efficiency. We just want to see that. And, I'm sure most of you have touched on it before, but you can elaborate on it now.
Shall I start? Yeah.
Yeah. Go ahead, Tony.
I think the high-tech drilling automation and data acquisition and advanced high-end rigs, yeah, that I haven't seen. I've seen technology certainly being used in drill bits, in bottom hole assembly components and things. I think there is an opportunity for custom built land rigs for the geothermal industry that really take some really good, data acquisition, enable AI. Some technologies they're new in oil and gas as well, but take them quickly to geothermal. so that they have a jump in ability quickly at relatively low cost. You know, software and technology applied in that arena. Yeah, I think that would help quickly. Yeah.
Maybe I could add some words in the same direction than Tony. In a recent project we had, we use MWD, measurement while drilling, which was the first time we did that during when we drill a geothermal well. And what we learned, it was gamma ray, which is a quite simple measurement of the natural total radioactivity. And we know in our basement where we have fault zone, generally we have clay formation, which is very rich in potassium. So generally we have a peak of potassium, and then because of the clay concentration and we dissolve primary minerals, we have secondary silica, which is deposit, which generally correspond to permeable zone. And then so we have a strong peak of potassium and then a strong decreasing of potassium, because primary silica, there is no, I would say, radioactive minerals. And when we did measurement while drilling, we were able to, in fact, locate those zones during the drilling and then to target some zone. So we are not obliged to wait to analyze the cutting, to make slab measurement, to make X-ray diffraction, complex geology measurement. We did that during the drilling, and then we save times, and also we decide on site if we stop or not some operation. So this simple measurement that you collect it directly during the drilling operation, we gain times and we save cost.
Mark, Lauren.
Yeah, so I couldn't agree more about real-time data collection, custom-built rigs. One thing that I would love to see is the opportunity to leverage some of the work that the oil and gas industry has done in how fluid is interacting with the rock away from the wellbore. We're doing some research, we're looking to do some research in this space. I know Mark is going to say multi-stimulation stimulation, so that's why I'm saying this instead, because I think that's just as critical. But I do think that there's a lot of really interesting work that has not been done that's been done in the oil and gas space, but not necessarily translated to geothermal in terms of controlling where fluid goes in the reservoir.
So I know this this panel is very interesting. We have lots of questions, but we don't have all the time. So we will try to wrap up. And for all of you, you just have about 1 minute, all the panelists, to just give your final thoughts on what big idea can make a difference in enhanced or engineered geothermal systems, EGS, and what can just bring us to that state of it being technically ready and commercially viable. So you have 1 minute to wrap up on that. So Mark, you were about to say something, so we could start with you.
Okay, well, again, I'll repeat myself. I think that multi-stage hydraulic stimulation techniques borrowed from shale are very promising. I'll also add, though, that those need to be optimized. So how close together do you put the wells? How many stages do you use? How many perf clusters do you use? How do you design the perf clusters? What kind of rates should you use proppant? So there's a whole universe of optimization questions that we've largely learned how to solve in shale that we are at the infancy of solving in EGS. So I think that's going to be taking those lessons from shale, but then adapting them to EGS and then figuring out how to do it in EGS is going to be great.
Okay, Ron.
Okay, yeah, so it's, I think from a stimulation perspective, I think we're going to be faced with trying to make real-time decisions based on real-time data, and that's both surface and subsurface data. So we can have fiber optics in the hole. We can look at what Mark's saying, cluster efficiency. We can start looking at optimizing the treatments to get the best distribution of fluids into the reservoir. So I see a big area there. But then on the completion side, high temperature seals that are going to hold up for the life of the well, reliable downhole flow control that's going to hold up for the life of the well, and then the monitoring. We just need to beef that technology up so that we can make it reliable, not just for days, months, but for years, and give us the data we need long term so that we can understand these reservoirs better and really enhance that thermal recovery. I think that's going to be the thing, is maximizing the efficiency of our completions.
Great. Lauren, you want to say something for 1 minute?
+1 to everything that was just said, but I'd go with, I'd love to see integrated downhole flow control with monitoring. And somebody build us a 300C geophone, please.
Okay. Tony.
Yeah, I think let's not wait for 300-degree, 400-degree C electronics. Let's design and build a drilling system that we at least push the temperature up 25, 50 degrees centigrade by using existing things that we have combined together with a few little technological jumps along that journey with insulation and cooling and whatever we need to do, so we can get into those hotter rocks and generate more heat for the EGS to do its stuff. Yeah.
All right. So Albert, I started with you, and I'll probably be ending with you. If you could just give us your 1-minute view on where EGS should be headed.
Yes, thank you, Rita. So I think for us, yes, it's a technology. So we need innovation, we need new ideas, we need a crossover between people, but we need also to lower the cost of project, because it's too expensive to have a more commercial project. But by doing that also, we need to be careful to manage projects by taking care about environment. For instance, in our case, we are doing zero emission plants. We are producing, we're taking, and we are reinjecting everything. There is no emission. So we need to calculate the life cycle assessment showing that the carbon footprint is very low, it's very important. And the second thing we have to take care also, which is not technical, is to take also into account, I would say, local people. So we need to better communicate, to explain, to educate, as you mentioned. It's very important, and to demonstrate, to show some realization. And then I would say what it has been also discussed today, but we need to scale up. One thing we are thinking, we are not today, we are doing doublet. We are thinking now to do from the same pad to do, for instance, 2 doublet, in order to maybe concentrate more flow rate on the same platform, and then you save cost. And it could also a future for us at least to have a bigger, larger project, but at the same location. So we expect to go in that direction.
All right. Thank you all. Thank you to my amazing panelists. Thank you to all who dialed in or logged in for this session. This is the Pivot 2021 Get Into Geothermal Anywhere, EGS Technoeconomics. Thank you very much. All right.
Thanks, everyone.